For this chapter, we're going to be looking at some paving mathematics as it applies to any kind of project. The learning objective is to demonstrate the practical application of mathematics as it relates to your project, your job, counting quantities, totals, yields, things like that. To start out with, let's talk about order of operations. I hope most of you have heard of the term PEMDAS. What does PEMDAS stand for? First, you perform any calculation inside any parentheses. That's the order of operations. We always do what's in parentheses first. After that, we move on to exponents. Once we've done the exponents portion of any formula calculation, we will move down to performing all multiplication and division in order from left to right. Then finally, we'll do any addition and subtraction in the same order, left to right. So that's just the order of operations of basic mathematical rules. So let's talk about some common paving math. I'm going to go through several different formulas here at the beginning of this presentation, and you'll notice there are several variables that stay constant, just oriented in different places with each formula. So I just want to point that out to you as we get going forward. As for example, the first formula here is for length of spread. And a constant that you see in this formula is 9. 9 represents how many square feet in 1 square yard. That 9 will always represent that in all these formulas, so you'll see it quite a bit. In this case, length of spread will equal 9 times T, T being total pounds. I want to point out that anytime we're doing a mathematical calculation, we're going to be dealing with pounds, but we are usually always going to want to convert the pounds to tons because we're dealing with an asphalt mixture that is talked about in tons, not in pounds. The width of the pavement. The width of the pavement, W here, could be how wide a total roadway or pavement is, or it could just be how wide your paver was laying a mat for that particular. All depends on how it's being used in the formula. And when it comes to application rate, that's straightforward. We call it an application rate, but it's basically the thickness of the pavement you're laying. So again, length of spread per ton. If you notice, the formula here on the right is almost the same as what we just showed you, but the difference is per ton. Guess what the constant is that we've added to this formula is 2,000, which also represents how many pounds are in 1 ton, 2,000 pounds per ton. Everything else remained the same. Now let's talk about number of tons required for a project or for a section or for whatever it may be. Again, when we're doing calculations in this case, T is representing tons in total, but we're always while we're doing our math, we will be using it in pounds and then have to convert it back when we're done with our calculation. When it comes to length of spread, the spread may be the total roadway. It could be, 2 miles, 6 mile, whatever roadway, or it could just be a day's production. It all depends on how you're doing, what you're trying to accomplish with your mathematical function. Again, with the pavement, with the spread stays the same, and of course application rate would pretty much depend on how thick you're laying your mat. Here's one, application rate. So we're trying to calculate the application rate. Notice how this formula on the right is changing very subtly, and you need to pay attention to these variables, how they change, the way they're oriented in these formulas. But for this particular one, we can apply the application, we can be calculating an application rate for a couple different things. If we're calculating it for asphalt, T in this case would be actually the pounds of asphalt that was used. Or if, say, we wanted to calculate it for our tack yield or our tack coat. In this case, tack is not a weighed in pounds, it's dealt with in gallons. So for this formula, same formula could be used to determine the gallons of tack emulsion that was used, or the pounds that can then be converted to tons of asphalt that was used. So you'll see this one as we go forward a couple different times. In this presentation, we're also going to address pavement placement limitations. Basically, what we're talking about here is how we use a nomograph. We'll show you how that's used and go over that. We're also going to talk about minimum transition lengths. When we say transition lengths, we're talking about if you're doing an overlay. For overlays, you can't just abruptly stop if you're doing a 2-inch overlay and just drop it off. You'll either have a bump if you're going over it that way, or you'll have a drop off if you're paving in the other direction. So we have to have transitions that'll make sure our roadways stay smooth. And VDOT has come up with a standard called the Asphalt Concrete Overlay Transition, or ACOT 1. We're going to talk about that in this presentation. And lastly, there'll be a separate presentation that will address VTM 137. There's a couple different methods, and you'll hear about that as a Part B related to the paving math associated with this chapter. So let's first start with the first one we talked about, which was length of spread. And if you remember the formula here, we were talking about when we're dealing with tons or with weight of a mixture, we're going to do our math in pounds, but as it relates here, you see that I've stated the pounds for this formula to be 132,940 pounds, but we never talk about asphalt in that format. We talk about it in tons. So that equates to 66.47 tons, which is more what we see. But when we're doing any math, talking about length of spread, we have to convert that tons to pounds. And that is what we've done here. The pavement width happens to be 26 feet wide, and the application rate was 170 pounds per square yard. Take our formula, add our variables where they relate, and work out our math. This math gave us a length of spread if we were placing a pavement 26 feet wide with an application rate of 170 pounds. It was 66.4 tons, would cover a distance of 270.7 feet minimum. So that's basically the math that we're talking about. And we're going to go through lots of formulas in this presentation and work them out. So just follow along as we go. Now let's talk about the length of spread per a single ton using the same scenario. When I say same scenario, we're still keeping the pounds, the pavement width, and the application rate as we had on the previous slide. And of course you see the note here that 1 ton equals 2,000 pounds. So that's why we switched to the formula. Instead of having T at the top, we have the 2,000 as a constant. We insert our variables, work out our calculation, and anytime I would be placing a pavement 170 pounds per square yard thickness at a pavement width of 26 feet, I would only be able to go, the length of that spread would only be 4.1 feet. Now let's look at the possible length per spread per truck. And I do want to note here, you see on the top of this slide, it says bonus problem number 1. There will be several problems as we go through this presentation, and if they're labeled as a bonus problem, that means they're not listed in your study guide or student manual. You may want to make some notes of these as a reference for when you're taking your exam, or for possible reference when you're doing your job, when you have these same type scenarios and variables available. So for the length of spread per truck, basically what we need to know is our truck capacity. Typical dump truck nowadays will haul around 20 tons. And we're pulling a paver width. The paver width happens to be 14 foot wide, and we're laying an application rate of 165 pounds per square yard, basically 1.5 inches. So for this scenario, the first thing we'd have to do is convert our tons to pounds to do our math, to calculate our formula. Straightforward, 1 ton, 2,000 pounds, so 20 tons times 2,000 is 40,000 pounds of material. Once we've made that conversion, we can input all our variables into our formula, and we can work this through the process, and it's going to tell us that if I'm laying a paver width of 14 foot wide at a application rate of 165 pounds per square yard, 20 tons, would go about 155.8 feet. So that's how we can figure this out and how long a load of asphalt would apply to this particular roadway. Now let's talk about the total tons of asphalt required for a roadway, basically a whole road. This road happens to be 2 miles long, and our application rate's back at 170 pounds per square yard. The pavement width is all the way across the pavement happens to be 26 feet wide. What's our total tons for this roadway going to be? Well, again, my length has to be in feet. I have to keep my units in the way they're set up in the formulas. I can't flip-flop back and forth. So the first thing I'll do is convert my 2 miles to feet. And we all know that 1 mile equals 5,280 feet. That's listed here on this slide. So the first thing I'll do is take that distance times 2 miles, and I'll end up with 10,560 feet. Once I've converted everything to feet, and I've got everything in the right units, I can go, insert my variables and do my calculation. And when we did that, we will see that I'm actually calculating a pounds here, not tons. The question was asking for tons, right? So what I've calculated with this formula is that I have over 5 million pounds of material. How do I convert those pounds back to tons? Basically, I know that there's 2,000 pounds in 1 ton, so I take that number, 5,186,133, divided by the 2,000 pounds per ton, will tell me that this roadway at 26 feet wide, 2 miles long, with 170 pounds per square yard application rate would take a minimum of 2,593 tons to pave this roadway. And so that's how you can convert back and forth between units. Now, if I've paved this roadway for 2,593 tons, but I need, what I need to know is how many truckloads of asphalt are required to pave it. And we'll just call it Route 123. Well, typical or average truck capacity is 20 tons. So how many loads is that going to take for me to accomplish this, complete this roadway? Well, first thing I got to do is I have a different formula here for truckloads. T is my tons of asphalt, which we've been given, 2,593, and we know that each truck can hold approximately 20 tons. So basically doing this calculation is telling me that I'll need 130 loads of asphalt if each load is approximately 20 tons to complete this roadway, to deliver enough material to complete this roadway to the project. So now that I know I needed 130 loads, how many cycles will I need if the project only has 13 trucks available to it? Well, what do I mean when I say cycles? Cycles is if I have 13 trucks, all 13 trucks will come to the project and basically place their load and before the first truck comes back again. So a full cycle is the completion of those 13 trucks. So how many cycles will every truck have to make to place 130 loads if I have 13 trucks? And basically you just divide it out and you'll see that it takes 10 cycles. So if I was placing on Route 123 a day and I wanted to place all 2,000 tons plus tons, I would need to make sure I can accommodate 10 cycles with 13 trucks to complete this roadway in 1 day. Now we went through a few problems that were in the book. You had a couple bonus problems thrown in, but there are some practice problems available in your study guide. I want you to take the time to complete these practice problems on page 4-5. And while you're doing this, I know you're watching the video. I want you to pause the video while you work these, because when we continue in this video, you will actually see the answers displayed on the next slide. So take a moment, pause everything, and work these problems out. Then you can check them to the answers provided to you in a moment. Welcome back, and here are the answers to the problems on page 4-5. I do want to note to you that if you had trouble with these problems are actually worked out in the appendix for chapter 4 in the back of your study guide. So you're not just supplied the answers here, you're supplied the actual mathematical problem worked out in the back of the book. So that's a good reference for you to look at as you continue through this chapter. But I'm not going to sit here and just read you the answers. I'll just be reading numbers to you. You can see what's provided for you on the slide. And if you had any problems with this, I do recommend you get with a friend, or you do some additional work. You can reach out to someone and get some assistance with this before continuing. Continuing on with this presentation, let's talk about how we can determine application rates. And for this portion of the presentation, we'll talk about a couple different kinds of application rates. It's the formula I mentioned at the beginning, where you can be dealing with the actual asphalt mix. And in that case, we'll be doing our calculations using pounds. Even though it may be referenced in tons, we'll convert it to pounds. Or if we're doing tack application, or our emulsion or tack, we will be dealing with it in gallons. So the same formula will be worked in both for both materials, just depends on what units we're actually using during the calculation. I do have a definition listed here, because you see that I'm saying this is a ex post calculation, which basically means that this type of calculation is used after the material's been placed, and it's basically to verify the right amount was placed, the right amount of tack or yield has been accomplished. So it's typically done as an ex post calculation. The basic calculation here is R is my application rate. Again, the constant of 9, how many square feet in a square yard. Again, with the total amount of material, whether it be pounds or gallons, whether I'm dealing with asphalt mix or if I'm dealing with an emulsion. Width it could be the full width of our roadway, or it could be the width of our distributor place if we were applying a tack coat. And of course, the length of the roadway or the length of the pool for that day. Here's an example problem for the tack coat. All right, in this case, we're dealing with gallons. We have 495 gallons for this example. The length of our roadway is 5,750 feet. The pavement width for this, or it could have been your distributor width, was 13 feet. And once we've done this calculation, we want to make sure that our tack yield, our tack applied rate is correct and that it meets specification. I do want to reference here that the VDOT Road and Bridge Specification, section 310.03, tells us that an approved application rate for tack coat is between 0.05 and 0.10 gallons per square yard. Our formula, we've seen it before, but here it is again. We're dealing with gallons. We're going to plug our variables in. Then we're going to do our standard math, and we'll find that our yield, or our application rate for this tack coat with these units and variables applied gives us a application rate of 0.06 gallons per square yard. And as also referenced previously, this does meet the specification required by VDOT of between a 0.05 and 0.1 gallon per square yard. So these variables would have met VDOT specification. Now let's look at application rate for asphalt. Again, I want to point out this is a bonus problem, so it's not in your book. If you want to have this for a reference, you may want to write this information down. But for this example, we're going to have a total amount of asphalt, 581 tons. Again, we deal with asphalt in tons, but for our calculation, we'll convert it to pounds. Length of the roadway was 5,280 feet, and the pavement width, or maybe our paver width as we were placing it 12 feet wide. We convert our tons to pounds. We got over 1 million pounds of material here. So here's our formula at the bottom portion of this slide, and we're just going to, now that we've converted it to pounds, we're going to insert our data and work out our calculation, and we'll find out that our application rate for this asphalt mixture was 165 pounds per square yard, or basically 1.5 inches if you're converting your pounds per square yard to inches. There is also, again, some practice problems. You'll see this slide several times through this presentation. Rather than working out all the math, we're going to ask you to pause the video, work your problems out. After you've worked your problems out, the answers will be displayed on the next slide. So again, pause your video and continue on. Welcome back. Here's the answers to your problems on page 4-7. Again, if you had any problems working these out, the math is shown to you in your appendix. So you can flip to the back of the manual and be able to see the actual math worked out. And if you had any other problems, you don't understand what you're looking at, we recommend you get with a friend or a coworker and see if they can help you with these particular problems. But I'm not going to read them. You can read your own answers and compare them to what you got. So now let's move forward and talk about some placement limitations. And there's different variables that can impact our placement limitations. One of the things we have to consider right off the bat is what mix type we're placing, whether it be a surface mix, an intermediate mix, or base mix. Our placement limitations for each mix are a little bit different, and all that's referenced in our specifications. Another variable that we have to make sure we consider is whether or not we're using a warm mix technology. And when I say technology, it can be a warm mix additive or it can be foaming. The introduction of water to foam is also considered a warm mix technology. So either one falls in what we consider a warm mix product, which affects what our placement limitations are. Another variable to consider, it depends on the base temperature. And what I mean when I say base temperature here, I'm actually talking about the surface of the material you're laying it on. The temperature of the material you're placing the new mat on impacts significantly our placement limitations, because that mat and that solid contact between the new mix and the previous substrate that we're laying it on will draw the temperature, will pull the heat out of the mix very quickly. So it's probably the most critical factor we have when talking about placement limitations. One thing to know is anytime that this base temperature is below 40 degrees Fahrenheit, there is no paving. You can't specification does not allow you to place any asphalt mix at any temperature when it's below 40 degrees that you're applying the mixture to. If I'm using a warm mix additive, as we mentioned up above, the limit for that surface I'm getting ready to apply the mix to has to be 40 and rising. So we would have to determine that the temperature is actually increasing a little bit, even though it's down near 40. But if I don't have a warm mix additive, what would that be? That's our typical hot mix, okay? If I ain't using a warm mix additive, then it has to be 50 degrees Fahrenheit and rising before I can place any mix. So let's continue on and talk about what happens if that base or that surface I'm getting ready to place this new mix on, temperature is anywhere between that 40 degrees, because if it's below 40, we're not placing anything, and 80. Well, there's something called a nomograph. That's what we're going to address at this point of the presentation and how this applies. You'll see as we go forward how we use this nomograph and how we're able to determine what our asphalt temperature has to be on the job site before we can place it. And we'll be covering that. But if we are using a warm mix additive, we do not apply the nomograph. The nomograph only applies to a hot mix product or a asphalt mixture that does not use a warm mix additive, because anything that doesn't use a warm mix technology, whether it be water, foaming, or additive, is hot mix. So everything else falls in this category. And And in that case, instead of using the nomograph, when we as a producer produce a product with a warm mix additive, the minimum laydown temperature for that mix when it arrives at the job site is 200 degrees Fahrenheit. As long as it's above that, we can place it. If it's below that, we cannot. So there's three things we need to know that affect placement limitations. One, I'm using the term here base temperature, or it could be surface temperature that I'm getting ready to apply the mix to. That's all the same. The second thing is the number of breakdown rollers, whether it be one or two. And what that means is if you only have one roller in the breakdown portion of your roller pattern, then you have different limitations than you do if you have two. And the way, when I say you'd have two breakdown rollers, what I mean is you're using two rollers side by side and they're basically working in tandem, or I said side by side, I'm basically following each other very closely. That would allow you a different time, as you'll see as we go forward with this nomograph. And the third variable that we need to know is the application rate, how thick the mix is we're placing it. So once we have these three variables, we apply them to the nomograph to determine our minimum laydown temperature. So we're going to continue on and talk about problem number 7, which is in your study guide, your workbook. For this particular problem, we have an application rate of 220 pounds per square yard. The base temperature, the surface that we're getting ready to apply our mix to, is 50 degrees Fahrenheit, and we have one breakdown roller. The way we use this nomograph is we work on it from right to left as you're seeing it on your screen. Far right is the base temperature, and our data told us that the base temperature is 50 degrees Fahrenheit. So we'll put a point at that at 50 degrees Fahrenheit. The next information we have available to us is we have one breakdown roller and our application rate is 220 pounds per square yard. So we see here in the middle of this nomograph, there's two different lines, two different grids. And since we have one breakdown roller, we're going to apply our point on the grid that is for a 15-minute max breakdown, rolling time using one roller, which is the first one going vertically straight up and down. And you see here the point was applied at our application rate of 220 pounds. Once we've applied those 2 points, it's basically play the game, connect the dots, but extend our line all the way over to our minimum laydown temperature. So you need a straight edge, whether it be a side of a book or something, but you basically get you a straight edge. You connect those 2 points and extend your line out. And what that is telling us is that our minimum laydown temperature is 295 degrees Fahrenheit. So any asphalt that comes out to the project that's below 295 degrees Fahrenheit should not be placed. It would have to be shipped back to the plant. Anything above it, we're good. And as far as the procedure on how to check your temperature of your truck, it's not one point. It's through multiple checks of the same load. And then the average of those multiple checks will give me a final temperature of the load when it's arrived to the job site. But what the nomograph is telling us is that the minimum temperature it can be before it is placed at the project, not at the plant, but at the project, is 295 degrees Fahrenheit. Now let's look at the next problem in our workbook, problem number 8. Again, same nomograph, just different variables. In this case, the application rate's 175 pounds per square yard. Base temperature's 40 and rising. It's right on the bottom, so it's much cooler. But because it's much cooler, looks like for this problem, they're giving us 2 breakdown rollers. So we apply the base temperature, 40 degrees. We'll put our point there, our dot. But now, since we have 2 breakdown rollers, we're going to apply our application rate on this angle line here, the other grid, which is an 8-minute max breakdown rolling time using 2 rollers, as it's labeled, and we'll apply that 175 pounds per square yard. You can see the point here in the middle of the screen showing that area. Again, connect the 2 dots, draw a line that we extend all the way over to the minimum laydown temperature, and that minimum laydown temperature happens to be 289 degrees Fahrenheit. So anything below that cannot be placed. As long as it's above it, we're good to go. Again, there's a couple practice problems that are in the back on this same page, on page 4-9. But these practice problems, you're probably going to see the answers here coming up on the next slide. So we asked you to pause the video, same as we've done previously, and then we'll display the answers for you here in just a second. Welcome back. Here's the answer to number 9. We had a situation where we had a base temperature, 45 degrees Fahrenheit, with one breakdown roller and an application rate of 185 pounds per square yard. We connected those dots, and it told us our minimum laydown temperature was 318 degrees Fahrenheit. For number 10, we actually, base temperature, or surface temperature was 52 degrees Fahrenheit. We had 2 breakdown rollers, so we're using the different grid here in the middle, and our application rate was 190 pounds per square yard, so our minimum laydown temperature was 274 degrees Fahrenheit. If you had any problems with these 2 nomographs, I do recommend you get with a colleague, a coworker, a friend, and do some more example problems. Now let's talk about overlay transition links. And when I mean an overlay transition, straightforward, the overlay means you didn't do any milling or anything that would allow you to lower your new pavement mat down to tie into something. So this could apply when it comes to an overlay that you're going to have to transition down to the existing mat in some way. So this would apply anytime you start or stop your overlay. It could be for bridge clearances. A lot of times on a lot of our primaries and interstates, we have minimum bridge clearances that have to be maintained. So we have to transition down. We don't always have milling for this, but we have to tie down and then come back up, start out on the other side of the bridge, but maintain that proper clearance. Well, these transition links need to be long enough that the pavement to the traveling public still remains smooth. Okay, and that's basically what we're going to be determining here, is how long these transitions need to be to keep a smooth pavement. What VDOT has determined is these transition links are based on 2 variables, primarily. The primary variables are speed and thickness of the overlay. So they developed a standard. This standard is called the Asphalt Concrete Overlay Transition, or the acronym, VDOT loves acronyms, is ACOT-1. Here on the next slide is a picture of ACOT-1, and on this whole form here, the main information we're after is this transition rate indicated with the yellow arrow. We're going to move forward with a couple example calculations, and you'll see how we apply this transition rate. The general formula for ACOT-1 is below here. And you can see from now that we've blown up this transition rate big enough that you can see it, it basically references based on speed of the posted speed limit for the roadway. It's not how fast the traveling public goes, it's the posted speed limit. It gives us a certain distance in feet, and then we apply it to the thickness of the overlay we're laying. So for a single lift overlay, the transition lift distance would basically be the rate, which comes from the speed we're going for feet per inch, times the thickness, which is the inches of how thick our overlay is. So for an example, if the speed limit, posted speed limit, is 65 miles per hour, and we're doing an overlay thickness at 2 inches, what would be our transition length? Well, if we apply the formula above it here and we look at this transition rate, our posted speed limit is 65. That tells us our rate is 45 feet per inch. And we was given the information of our overlay thickness being 2 inches, so 45 times 2, as we work through this calculation, tells us that we need a minimum transition length of 90 feet to maintain a smooth riding pavement. Well, what happens when we have 2 lifts? And when I say that, maybe we're doing a lift of IM and then a lift of surface, and it's all overlay. We had to adjust our formula. We have to account for the first lift and then the second lift, and all we'll do is add these 2 transition links together. For this example, the posted speed limit is 55 miles per hour. Lift 1 happens to be 2 inches thick, and lift 2, for convenience, just happens to be 2 inches thick as well. So when we work out this particular equation, we'll realize that the 55 miles per hour tells us our transition length is 40 feet, it's 2 inches thick. All right, we work this out, when we add the two together, we'll find out that our total transition distance would be 160 feet in this case. You see how this works out? As we added the first lift and second lift together, which have been 80 plus 80, will give us 160 feet. Again, you've seen this several times. There are some practice problems in your study guide on page 412. We asked you to pause the video, work through these problems, as you'll be given the answers on the next slide. Welcome back. Here are the answers to the problems on page 4-12. For number 12, your transition length happened to be 100 feet. And for problem 13, your transition length happened to be 140 feet. If you had any problems with these, get with a coworker, get with a friend, and see if you can figure it out and get some more practice problems to work with. With that, if you have any other questions, work with a coworker, or you can actually email Germana. They're a great resource to help you with these problems. But we appreciate your time and wish you a good day.